We have 2 sections of material left in this class, and they're both in Chapter 5. And we're going to move our discussion away from whole numbers and broaden it a little bit into integers. That's what's going to happen in Chapter 5. So we've been talking about whole numbers, when you talk about integers, and so the very first place we're going to start is what in the world is an integer. So we've talked about them briefly back in, I think it was Chapter 2. Do you remember what we described integers as being? How are they different than whole numbers? You get negatives, right? You don't get anything else, though. So there's no fractions or decimals in integers, but you do get the negatives. So the integers, your book uses the capital I as the notation. That is actually not what most books use. So if you were seeing this in another book, you might see Z used. Z is what's usually used for integers. And this is the set, and I'll put ... here, of all the negative and positive numbers that we've been working with, namely the whole numbers. And then we've also got, of course, 0 in there because it's a whole number. Okay, so these are the integers. Thankfully, when we work with integers, a lot of the things that we do with them are the same as whole numbers. We're going to get to some properties of whole number of integers in a little bit. But before, we're going to actually talk about how we go about adding integers. And what I want to show you is I want to show you some concrete models for how you can work with students to understand why it is that we have the rules that we do when we do integer addition. Okay, so we're starting with addition. All right, so the first model is called the chip model. Okay, so if you have in your hands or in your bag or whatever some other color of pen or pencil than you currently are using, grab it. Okay, if you don't, maybe the person next to you will let you borrow theirs. So highlighter, crayon, colored marker, something else besides what you're working with, okay? And if you want 2 of those such things, because you guys are education people and sometimes you have lots of colorful things in your bag, that's cool. You can do that, okay? So you need 2 colors, the one you're working with and something else at the least. All right, what the chip model does is we're going to put everything inside of this circle, and our values that are positive are going to have one color, and our values that are negative are going to have another color. So you can pick which color it is you use. You just need to make sure that whatever you're picking, you're kind of going to tell me what it is. So for instance, if I decide that I want to use red for my negatives, I'm really not sure why it looks so funny. It's not really circular. It's weird. Go with that. It's a little bit better. So there's my red. My red's going to represent negatives. And I'm going to use yellow today to represent my positives because I have lots of colors. So that's my pick. Okay? So here's the way this works. Inside of the circle, we're going to put 5 yellow chips because I have 5 as my number. So I've got 1, 2, 3, 4, 5 yellow chips. I add them, I put them inside of the circle. I collect them into my Ziploc baggie or whatever. Okay? And then what do you think I'm going to do? Well, I'm not going to mark them out. I'm adding, so I'm going to add in 3 of the red chips, whatever your color was. So I've got 3 red chips, 5 yellow chips in the bag. Okay? This is where you start. And then what you do is you would talk to your children that you're working with about the fact that a yellow chip and a red chip are the same number, but they're opposite each other. Right? One's positive, one's negative. They're opposite each other. So when I combine them, they cancel each other out. Right? They combine and they equal the number 0. So 2 of these equals 0, 2 of these, and 2 of these. So in some sense, we're removing the pairs that are equal to 0. These are 0 pairs. And you'll hear that phrase used sometimes, 0 pairs. So where does that leave us? Well, it leaves us with the same circle that we had before, but what's in it now? Just 2 yellows, that's all. And what value is that? I mean, these are equal. The first one's equal to the second one. What number value does this equal? 2. Positive or negative? Positive, because my yellow chips are my positive number. Okay. If you didn't have colored something with you, you could make one hollow and one filled in. That's another thing you could do. So one's empty and one's solid. Okay. So addition is this idea of adding everything into the pot and then removing 0 pairs, things that are adding up to 0. This chip model, okay? The next one looks almost the same, but it doesn't necessarily require you to have colors, okay? This is called the charged fields model. And what this model does is it takes our numbers and it assigns them a charge. So, so for instance, a positive number has a positive charge, a negative number has a negative charge. So when I see 5, I write in 5 positives. And if you really want to write them in colors, you could, but the positive part actually tells you that it's positive. And then I write in 3 negatives because there is a negative 3 at the end. And then I do the exact same thing I just did on the other slide. I remove 0 pairs. So I pair these up in zeros, and I remove them. And when I do that, I end up with circle with what inside? 2 positives, which is the number 2. Now, if you were working with children, that first one is very concrete because you can physically use chips, like poker chip kind of things, right? I've seen them before, actually like this, like in the teacher manipulative purchase kind of things you can buy at the supply stores and whatever, where they have it colored on one side red and one side yellow. Red and yellow are usually the ones they actually use, or maybe red and black sometimes too. And so you can actually use them on either side then, which kind of makes them dual purpose. You have fewer chips that you need. But you could also use just poker chips. I mean, that's probably cheaper than buying the teacher education stuff, and you actually have some reds, some greens, some blues, some black, whatever the colors are, and you could say that this color is the negative and this color is the positive. So the kids actually can touch them, right? They can feel them, they can work with them. And so that's a really helpful thing to be able to do. The positive negativeness is a little bit more abstract. You recognize, looking at this, that this picture is the same picture I did on the other slide, right? But there's really not a hands-on stuff to do with this. All I could do is draw the picture. Are you with me? The other picture I drew was actually just a picture of what you would really do with poker chips. This one, that's not what it is. It really is just a picture with pluses and minuses in it. So there's a little bit more abstraction to this one. Let's do another one. There's 2 more. Let's do another one. Number line model. Number line model also is a little bit more abstract, but it does have a concreteness to it. And for those of you who have kinetic learners, do you know what that is? What's kinetics? The hands-on, they want to move around, they want to do something hands-on, right? This works really well too, so I'll show you how to do it from that perspective after I show you how to do it on the paper. All right, so what this is actually telling us is we're going to create a number line. Our number line starts at 0, and the 5 at the beginning tells me I need to move out to 5. So in some sense, I have done something like this. I'll use a different color. I'll use blue. I've moved over here to 5. Moved 5, okay? And then what do you suppose this right here means? The negative 3 at the end. Go backwards 3, right? So if I go backwards 3 from the 5 where I am, that puts me here at 2. So forward 5, backward 3 leaves me at 2. All right, so how does this look if you actually had a kid who wanted to actually hands-on do something? Well, there's lots of things you could do. This classroom is arranged in rows, so it works really well. So Kaylee, you and I are in row 0, okay? We're starting at 0. And we're going to move 5 rows towards Sydney, okay? So I've got row 1, row 2, row 3, row 4, row 5. Okay, so I'm 5 away from where I started. Then I'm going to go backward 3, right? So I've got 1, 2, 3. And the question is, how far am I from where I started? I'm 2 away, 2 rows away from where I started. So you could actually do this with movement in your classroom as well. So for some kids, this might be a good, helpful option. All right, here's the next one. This is the most in your head one. Let's say it that way. It's the one that is going to be most appealing to kids who like to play with numbers. And maybe that's none of you guys in here today, but some kids really do. It looks like a puzzle. Okay, so this is going to appeal to some kids like that. So what we're going to do is we're going to start out with addition that we know how to do, something like 5 plus 2. They're whole numbers. We know how to do 5 plus 2. So what's 5 plus 2? It's 7. And then we're going to go to 5 plus 1. Again, still know how to do that. What's 5 plus 1? 6. And again, we're going to go down one more because I can still do 5 plus 0 with what I've known before, and that would be 5. Now, the next value that I'm going to go to is 5 plus negative 1, because what I'm doing in the middle here is I'm decreasing the number I'm adding by 1 every time. Now, I don't really want you to add 5 plus negative 1. What I want you to do is to notice this pattern goes 7, 6, 5, which means the answer next is 4. It's a pattern. And we could go to 5 plus negative 2, the next number back on a number line or in value. Again, 7, 6, 5, 4, and then it would be 3. And then your last one, the one that we actually care about because it's our problem, down this list of numbers, 7, 6, 5, 4, 3, 2. So our answer would be 2 based on setting up a pattern with prior knowledge. Does that make sense? It's not terribly difficult, but it's definitely not concrete, touch and feel kind of stuff, right? It's not. All right, this is going to feel a little bit awkwardly placed, but that's okay. It's related to what we're doing. Absolute value. Absolute value. So let's write down the definition first, and then we'll talk about it from a maybe like a picture point of view or graphical point of view. Absolute value for any integer x. The absolute value of x is equal to itself, x, if x is greater than or equal to 0. And it's equal to negative x if x is less than 0. It always feels a little bit awkward to write this statement down for students, because it looks like this is saying that the answer that comes out of this is negative. That's what it looks like, right? On the right-hand side, I have negative x. And that's probably not what you remember about absolute values. What do you remember about absolute values?
It's the distance away from 0, so it's
Always positive. So absolute value should always give me a positive answer. And the absolute value is a distance away from something. That's how we think about that, too. So how in the world is this definition, the second part, going to make sense? Because it says negative x on there. Let's look at the conditions in the end. First line. What kinds of numbers are we talking about in that first line? Positive. Or 0, right, Sydney? So this top line is talking about 0, 1, 2, 3, and so forth. It's the whole numbers, isn't it? It's the whole numbers in the first line. Okay, so if you have a whole number and you take its absolute value, you get the whole number. That's what that says. What kind of numbers are on the second line? What are you trying to tell me, Cassidy?
like 0 and then negative.
Okay, we don't get to include the 0 because it doesn't say or equal to, but the other part of what you're saying is right there. It's the negatives, right? So we're looking at things like, give me an example. -1 and -2 and -3. And so on, right? Okay, so let's take one of those. Let's just take -2. By this definition, it says that the absolute value of -2 should be negative of -2. What happens? It becomes a positive. And why did that happen? Because the numbers were negative to start with, right? So it doesn't give me any negative numbers. What this sign really says is it says that the sign on our numbers, which is negative, because this is only true when it's the negative numbers, changes. Okay? Because when I multiply negatives together, that actually ends up becoming a positive value. Negative and a negative is a positive, which is actually, this is kind of funny placement here because we actually haven't talked about that. It happens in section 2, but 5.2. Any questions on that? So this isn't different than what you've seen before. They're just structuring the language a little bit in a way that feels uncomfortable. It is the way that the language is normally structured, but we usually kind of just gloss over it and talk about removing negatives when we talk about absolute values. We just kind of ignore this language involved. Let's do some examples where we have to think about the absolute value. It says to classify the following as true or false, and if it's false, we're going to show a counter example. What in the world does counter example mean? We've had this happen before. Yeah, it's an example that shows it's false. That's all a counter example is. So I'd like for you to go through, take a look at those 4. Speculate which ones you think are true or false. Okay? Write down T or F, hopefully in a pencil so that we can change it if we need to. Give your best guess as to which one's what. And then we're going to talk about them. A and B look kind of alike, right? But you got to have this sort of sneaky suspicion in the back of your mind that there must be something going on different about them, right? Or they wouldn't put them both on there. Come on, you guys know how math books work, right? There's got to be something different about them, so keep that in mind. C and D kind of look alike as well. Again, you think about what it is that they're trying to get at by showing you both of those. What do you think on part A? Is it true or is it false? I agree. It is a true statement. Why does it make sense that if an x to the 4th is an absolute values that we can just remove the absolute values? Why does that work? It's a distance away from 0, okay. But why both the definitions, like I have 2 definitions for absolute value over here. It's greater than what? It is greater than or equal to 0. So why is x to the 4th automatically greater than or equal to 0?
Because you're multiplying an even number of times.
Right. So if I had a positive number and I multiplied it by itself, it's still positive. It's always negative numbers that make us a little bit concerned. So what happens when I take a negative number and multiply it by itself 4 times? It's positive, right? So this x to the 4th, whatever x is a positive number because I'm doing it to itself 4 times. So it is appropriate for it to be along the lines of this first definition where I simply lift the absolute values off, right? Because it's a positive number. That's what's going on there. How about the second one, true or false? That is a false statement. If we're finding out that it's false, we need to give an example as to why. So what did you let x be to show that this doesn't work? Okay. I think we could probably just do -2. Would that be okay? Okay. So does your paper say cubed or to the 5th? It does say 5th? Okay. All right, so -2 will work. 5th is what you meant, Amanda. Okay, that's fine. So -2 will work as the x value. So the question is then, if I put the -2 in on both sides, do I get the same thing? That's the question of the day, is do these equal if I let x be -2? All right, now both sides have -2 in parentheses power 5, right? Both sides have that piece the same. So what is -2 times itself 5 times? First of all, sign. Is it positive or negative? It's negative. What's the value of 2 times 2 times 2 times 2 times 2? 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is, you guys got it, it's 32. All right, so right now, on the right-hand side, it's just flat out -32. On the left-hand side, I have a -32 inside of an absolute value. Are those the same? No. What's the left-hand side equal to? Positive 32. So these are not equal. because on the left-hand side here, the answer is 32, whereas on the right-hand side here, it's negative 32. What's the difference between A and B? Why did one of them work and the other one didn't? Even and odd, right? It's how many times I'm multiplying something by itself. If you multiply something by itself an even number of times, everything becomes positive. And if you multiply something by itself an odd number of times, it takes whatever sign you started with. If it was positive, it stays positive. If it was negative, it stays negative. Okay, good job. All right, what in the world is different about the descriptions given in C and D? There must be something different, or I wouldn't have put them there, and then the book wouldn't have done it that way either, right?
Well, you're saying the same thing. You're
Am I?
being wordy about it.
Oh, Madison, am I wordy sometimes?
Well, because you're putting not negative.
Okay. But does not negative mean positive? That's the question. Ooh, somebody said something. Tira said, what about 0? It could be 0. What could be 0, Tira? The one in C or the one in D?
What? On C?
On C, right? Not negative isn't just the positives, it's also 0, right? Okay, so this one right here, it means 0 or positives. Are you guys with me? I have the possibility of something equaling 0. So let's look at part D first, since it doesn't have the 0 possibility. It just says positives. Is the absolute value of x always positive? No. It can't be negative, though, either. So this is false. It's not always positive. But why not? Because it could be 0. I know that looks like 101. It's not. It's the absolute value of 0. The absolute value of 0 is not positive, is it? It's 0. Right? The distance that the starting point is away from the starting point is 0. Okay? So let's go back up to part C then. Is it true that the absolute value of x is always 0 or positive? Yeah, that's true. So non-negative, although it sounded wordier, is really quite helpful because it included something that positive did not include. It included that 0. Any questions on that one? Okay. I mentioned this at the beginning that we were going to talk about some properties. These are all properties that we've seen before. So I want you to remind yourself, by writing them down, what are those properties? I'll fill them in afterwards, make sure everybody's on the same page. What is the closure property? What is the commutative property? What's associative? And what's identity? And if you don't remember one, it's okay. Leave it blank. We'll get it filled in. But remember the ones you can, write them in. Okay? Write down what you remember the closure, commutative, associative, and identity properties are. For whole numbers. We didn't for whole numbers, but they look the same for integers. Okay, we don't have to necessarily go in order. So somebody tell me one of them that you remember and feel pretty good about. Just one of them. Who would like to talk? Jessica, can you remember commutative? What does commutative say?
A plus B equals B plus A.
Do you guys agree with Jessica? Is that good? Okay, great. Yep, that's the community property. Tell me another one that you feel good about. Someone over here. Abby? Associative? Okay, what do you have for associative?
A plus B plus C, and then A and B are in parentheses.
Okay, like this?
Yeah.
Okay.
Equals A plus B plus C, and B and C are in parentheses.
Okay, do you agree with her? Good job. That's the associative property. Amanda?
For closure, an integer plus an integer will equal an integer.
Okay, so A plus B is a, and we use the word unique every time we did it, so we'll use it here again. It is a unique integer. And we don't have to worry about making the condition about the numbers being integers to begin with because we put it up here at the beginning. So we have it there. Okay? So closure again is the idea if we had all the numbers floating around in the room and I took two of them and added them together, I wouldn't end up with, say, a fraction. Right? I'd still end up with another integer. Add two integers together, you get another integer. All right, there's one last one on the bottom here. I almost don't have space to write. What does this one say on the bottom? Identity property of addition.
A plus B plus C plus 0. Plus C. Is that how you do it? Or
Yeah, I think we don't need the A plus B plus C. We can probably just do A plus 0 to make the point. So A plus 0. There was this sort of weird thing with identity that said that it needs to work in either order. Remember that? So A plus 0 or 0 plus A have to equal the A value we started with. So addition in either order is that property. Okay, is everyone good with that one? Can we get a new property with integers that we never had before? Here's the property, theorem 5.2. Additive inverse property says, for every integer A, there exists a unique integer negative A. It's called the additive inverse. Such that A plus negative A, or negative A plus A, either order of those added together, both equal one another and they equal 0. We would know they equal one another automatically because it's commutativity, right? So we get that part already. It's the equaling 0 part that's the important part of this. So yeah, we have to add them in either order, but it's the equaling 0 part. Why did we not have this property before today?
We didn't have negative.
You got it. We didn't have negative numbers. This property hinges upon the ability to have a number's opposite, a negative. And whole numbers don't have that, right? So this is a unique property to integers that we have not had before. All right, let's do one more theorem real quick, and then we'll stop. Theorem 5.3. Theorem 5.3 tells us some facts about integers that we're going to need and going to be able to be using. We'll justify more about the first one anyway in the next chapter in 5.2, section 5.2. The first one says if you have integers a, b, and c, if you do the opposite of a negative a, it's equal to a. The opposite of negative is positive. That's all that says. I know we always say something like a negative times a negative equals a positive. You think of it that way. But really, this is just saying the opposite of a negative. Well, what's the opposite of a negative? A positive, right? It is. All right, the second one says if a and b are equal to each other, then we can add a value c on both sides. Okay? We had this property before. It was called the additive property of equality. But we've got it for integers as well. The last one is unique. That one's different. It says that if I have negative a plus a negative b, this is equal to the negative of a plus b. And we could talk about from a CHIPS perspective, chip model perspective, why that has to happen really easily and really quickly. Let's just let a be 1 and b be 2, so I don't have to draw as many chips. And let's let our negatives be the red ones that I had before, okay? So let me get my red chips back. So this one actually is saying I have one red chip because it's negative 1. And I'm supposed to add in, and it says negative 2, which means I add in 2 red chips. And the combined total of that is negative, because it's all negative, and there's 3 chips. So it's almost like we're saying on this, we can count up the values a plus b, just count up how many we have, and the answer is going to be negative because they were all negative chips to start with. Make sense? All right, we'll stop there today.